the package I will be explaining in details it has been created 2 years ago, but stays below radars for most of the people in the community. And actually, I see this as a lack of advertisement and lack of the being present in the and on Slack, but I actually not yet convinced myself that this is the right design for this package. So this is something that builds. It's called AlgebraPDF. PDF here is not for the extension of the file, but rather for the probability density functions. So it's a kind of RooFit package. So it has all of the most of the features that we use, and it has been used already in LHCb analysis and more recently in few more. So actually, that's why I need the feedback from the community, and I really hope, how many of us? 20. So tonight I'm gonna have 20 issues. Well, that would be ideal, because what is really needed is to understand how people gonna use it, and from experts on Julia to see if it's a right design. So I will show you the core component for handling parameters and tuples, and at early stages I made this choice. However, there was I was not convinced that this is going to work fast, and inspired by Jerry talk, I wanted to bring it up again, and maybe it's actually going to be fast in the next Julia version. But let me show you in details. Another thing I would really appreciated the custom tutorial yesterday, where I realized that actually example cannot be too simple. So it's really nice to see that you learn a lot by making things simple. That's why I'm going to focus on simple example today. So essentially, AlgebraPDF is a registered Julia package, and you can just call using, and then we'll bring you the latest version. And then there is a range of packages that I also import that will be used. And then you start simple by saying, I want a Gaussian function, and it pulls you the Gaussian function. And what actually you give is the name of your parameters. So here the n tuple for the name stands registers parameters as their names that are going to be accessed by the symbols later. So the first one is going to be the mean, and the second one is the width. And now this structure is actually very light. So there is a dispatch on the name of the type. So Gaussian knows how to compute the Gaussian function, and then it has a name of the parameters in the type. And then it works perfectly with the plotting recipe. You can say, now plot my Gaussian from -4 to 7. Fine, you have it. And what we need for the PDF is normalization, and normalization is just a wrapper, essentially is another type that has nothing inside, rather than line shape and limits. So line shape is your Gaussian, and then the limits where the function is defined. So actually in the HAP, we almost never have a analytic CDF. The reason for that is that we always use truncated ranges. So we want our Gaussian, which has often skewed, but also defined in the specific ranges where normalization has to be computed numerically. And this is the approach that this package takes. So all of the normalizations are computed numerically in optimized way. So if you need several values from these functions, you wouldn't compute normalization several times. So it's once, because it's fixed. It depends on the parameters only. But here you see it's not that different to the previous one, but normalization now is ensured. And then once you have a ranges, since this guy has now ranges defined, you don't need to specify when you plot. So you say plot Gaussian, normalized Gaussian, and then it knows in rechanges. Fine. So that works straightforwardly. Now now we want a background to our signal, and always the standard case is the exponential function. Here you call the exponent, and then you pass the slope parameter, you normalize that, and you are able to plot. So it's exponent in the same ranges. So now you want to combine the two. You say fsum, first component, second component, and normalizations, and then you have a combined PDF. So here note that n in the name I used to indicate that it's normalized. That's why actually these numbers are numbers that stands in front of the PDF. So these are the PDF is going to have, so the function that I defined as the model has the names it has a normalization, correct normalization. So components are easy to plot and so on. Right, fine. Now a little bit of the internal. So let's explore what our model is. Essentially, it's now some object which has a vector, static vector of the components, and then static vector of weights, normalizations. And then both of the components are normalized functions with the parameters and the ranges, fine. And then you can ask model what are its parameters, and then you see all of them. You can evaluate model at the point. You can broadcast the model over the range. You can call the model with the list of parameters. You can change them here. So essentially what you have been defining before is not just the name of the parameters, but also their default values. So if you don't provide any parameter, then it will use default. And then if you want to change them, you change that. So here you see that 3 functions, default one, slightly updated when you pass one, and then much updated. So there's this method update parameters. That's since the objects are immutable, so we have to copy the object. Right, sampling is straightforward. Then it's also done numerically using the inverse numerical method. And you just say, well, rand model and then number of entries, and it does it in rather short time. But what actually I wanted to demonstrate is how it's done, because it's easy to follow. Inside, it creates the binned density. So essentially, here's a CDF, and you bin it. And if you have only 10 bins for the CDF, you're going to have, the generated function is going to be that ugly. But once you get even 50 points, it's just as good as the analytic inversion. So you don't see the binning. So the standard, the value that is used by default is 100, but you can adjust it. In most of cases, it's sufficient, and it's super quick actually. So you see that depending on number of bins, of course, it scales, but it's rather quick. Now then, likelihood is something we need for the fitting, and it's as simple as calling. So essentially, the model now is this model object, and you can call log on this model, and that's going to be log PDF, and then you can sum this over data. And it will give you a number. But in order to keep parameter dependencies, so you wrap it as a logarithmic. So essentially, time passes quick. So I will have to come quickly to the. Well, what I want to say, since you have it running, so please explore the notebook, and it can fit. So here you see it, how the fit result looks like. For internals, I actually wanted one thing I would like to discuss with expert. Please approach me if you have an opinion. Is that n-tuples? So it all works based on n-tuples. There is algebra of n-tuples inside of the parameters. So you combine n-tuples to have a total number of parameters. You can remove, replace parameters. So here's the default value. Here's the update comes. And then what that results is actually updated n-tuple. So it's actually part of the Julia. Julia can do that without much of the further code.
But I'm sure that's not.
No, the minus cannot. Minus.
No, even the plus. Someone defined.
You need a microphone because otherwise people cannot hear the discussion.
No, it's like what it's called is
Sorry,
the union inside. I mean, it's not.
Right. But if you just open the Julia session and you try to add 2 name tuple together, it's gonna throw in.
Yeah, right. But
so something
the plus is replaced to the union inside.
Wait, so are these normal Julia name tuple or not?
Yes.
Then someone's committing type piracy. I mean, you can, but it is the piracy. Well, okay, we can talk about this later.
Yeah, we should.
I just want to point out this is not the normal Julia behavior.
Yeah, guys, please, let's talk about that. And then another name tuples turn out to be nice construction. And then in order to fix the parameters, here is a purely exploratory. So one thing that I created is the construction that is flagged name tuple, which tells which parameters are fixed, which are released, and it behaves like n tuples, just keeping this flag for the names. And we should discuss how it works, but practically as an end user, it's super convenient. You can now fix parameters, you can update their values, and the feed, when you feed, would not know about the fixed parameters. So it would only deal with the free parameters. All right, so two things that I asked Chairman to give me chance to point is that in my field, in hadron spectroscopy, we will never be satisfied with the range of the PDF that are standardized, because we always invent something new. So it should be a very easy way to code your own PDF, and it's actually straightforward in this framework. So you with this library, once you have a function that depends on the x and the parameter, you can wrap it to the function with parameter and then use it as the standard thing. So as the normalize and utilize, so multiply and extend as you want. Chi-square fitting, fine. Let me show you what I originally planned to show. And this is framework. This is the set of libraries that help with the angular analysis of the decays. In hadron physics, we have a particle with a spin decays to the range of the final state particle, and we have a way to model this decay. So one simple example is a 3-body decay, where you all know probably Dalitz plot representation. So this is a kinematic space of all possible outcomes of the reactions, where the bands indicate in intermediate resonances. And there is a package 3-BodyDecays, which turned out to be extremely useful to understand your dynamics and to model that. And then recently, it's a numerical package, right? But recently I discovered that you can just pass the SymPy object and it will give you SymPy expression for the density. It's pretty amazing. So you don't need much to change the code inside. So we just pass the object, and then you're going to get nice symbolic expression. What I had to do is to redefine how Clebsch is computed, that are not fractional numbers but are rational, and then that's actually extension. That's the only extension that you need to have a nice symbolic expression for the. And the last thing I would like to point is that these standards are extremely important that we discussed already. But in amplitude analysis, we'll never be able to confine to standard densities. That's why the approach that we're investigating now is actually to preserve the symbolic expression for the model. Entire symbolic expression, SymPy provides one of the languages actually in which you can view your form. And the recent exploratory analysis in that direction that has been published, I encourage you to look at this link, recent analysis, because I had a talented student who showed how the analysis actually in LHCb, how the preservation should look like. So entire analysis is reproducible, and this is a page, in a build page in Docs in Swing, and it has a nice HTML interface with all steps, and Julia cross-checked it here. That and one thing that all of the expressions, that all of the code that you make is actually LaTeX because it's a SymPy. So the model building is done on the SymPy that is converted to JAX, and that makes very nice way of reviewing a model and seeing, as well as gives the possibility to preserve it. That can be handled to other people. Okay, that's very quickly what I want to say, but let's.
Excellent. Okay, let's thank Misha for that interesting talk.